Hello everyone, my name is Kirby Pollard, and today I'll be demonstrating Mathigon Polypad, a free digital mathematics tool that allows students to explore mathematical concepts through interactive models and visual representations. In my Algebra 1 unit, the student investigates different representations of linear functions, including tables, graphs, coordinate points, equations, and verbal descriptions. Rather than memorizing procedures, students actively construct and compare these representations to develop a deeper conceptual understanding. This lesson demonstrates the understanding by design framework by helping students answer the essential question: how can the same linear relationship be represented in different ways? To begin, open any web browser and navigate to mathigon.org Polypad. Polypad is free to use and does not require any software installation. Students can begin exploring immediately without creating an account. However, if students want to save their work, they should click sign in and create a free account using Google, Microsoft, or an email address. So I'm going to go ahead and log in. As you can see, once you log in, your save option becomes available. Once logged in, the home page opens to a blank workspace with a toolbar located at the left side of the screen. I'm going to go ahead and click Start New Polypad so that we can see that toolbar that'll be located at the screen. Here's the toolpad. Let's become familiar with the workspace. I'll start by at the bottom. We use the Move tool to move objects, the Drawing tool to draw, highlight, use a ruler or erase, and the Construction tool to plot points or lines. We also have the Equation tool here, which I'll demonstrate. If I wanted to write a linear equation, it will just support me in writing the linear equation in a way that is represented on my paper as well. I'll demonstrate how to pull up the coordinate plane. You drag and drop in the table. Starting with the coordinate plane, if I wanted to change my y and x axis view, I simply drag the points on the side or the bottom to increase. And then if I wanted to change my scaling, I change that to whatever I want the scale to be. For your table, if you select transpose, it'll change the view from vertical to horizontal. That depends on your preference or what you're showing your students. And to input their coordinate points, they simply double click and type those in. So if they were presented with a table, they could type in those coordinate points. And then using that drawing tool, which I selected earlier, or the construction tools, they could select the points on the coordinate plane. So for example, if I wanted to put 1, 2, I go to point 1, 2, 1, 2, and I select it. 2, 4, 2, 4, and I select it. Then I can use my line tool to construct the line. The other neat thing about it, if I select the move tool and I select my table, this blue arrow, if I drag it to the table or if I drag it to the coordinate plane, it will plot those points for me. So if students made an incorrect point, this would show them. So for example, I'm going to change my coordinate plane I'm going to change my table. I'm going to put 1, 3 instead. And as you can see, because my point was 1, 3 instead of 1, 2, it showed me that I made an error. So it allows students to reflect as well. But now I'm going to demonstrate how I use Polypad during instruction, showing you all the tools that I just demonstrated here and how they would fit into instruction for this. So I'm going to clear my workspace. You can do so by selecting each and just clicking delete. Or if I wanted to delete multiple things, I can drag and drop and highlight what I want deleted and then click delete, and it should delete everything. So suppose the students were given the linear equation y equals 2x plus 3, which I'll write here. This is my equation. I could make it bigger or smaller, and I can move it so that it's in the center of my workspace. Instead of immediately graphing the equations, students will build multiple representations. So step one, I might have them create a table. So they would go under the Algebra tab, under Coordinate Access and Tables tab, and then drag and drop that table over. They could work it by hand on the workspace. So if my first coordinate point was, or my x value was 1, 2 times 1 plus 3 equals 2 times 1 is 2 plus 3 equals 5. So now they have their first point. So they know 1, 5. Or you could have the students work on it in their notebooks so that they don't have to utilize the workspace. It's all about what we want our students or their preference that they like. So to fill out the rest of this table some more, I'm going to actually go 0, 3. So we can start from the origin. To add more spaces, just click enter. And then I'm going to go one more, which is 3, 9. Students should notice that the output increases by 2 each time. You could have them use that same tool. Plus 2, plus 2, plus 2. This reinforces the idea of a constant rate of change. Students can see that there was a plus 2 rate of change each time. Step 2 would be plot ordered pairs. So that's where we would pull out this coordinate plane. First, we would ensure that we have the appropriate y and x values represented. For here, my y goes all the way to 9 and my x goes to 3. So for that, for my x values, I'm covered. But for my y values, I may need to increase my graph. So I'm going to simply pull up and then down some more. And over on the side, if you find that your space is too small, you can zoom out to give you a little bit more space. So I see 9 at the top. And then just for consistency, I'll try to get to -9 down below. Using the point tool, they plot each ordered pair for the table. And as students place the points, they begin to notice that the points lie on a straight line. So we'll use our construction tool. We'll click point, and then we'll start to input these coordinate pairs onto this coordinate plane. So 0, 3, 0, 3, 1, 5, 2, 7, 3, 9. You may also want your students to put some negative numbers so that they can have a negative point, but for this demonstration, I focused on the positive. So after step 2, where they plotted the ordered pairs, step 3 is to draw the linear relationship. Under that same construction tool, they click line, they select their first point and their ending point. But you have to have at least 2 points to represent a line. And they connect their points. The graph now visually represents the equation. At this point, I would ask students, what patterns do you notice? How does the graph match your table? Where do you see the slope? And where is the y-intercept? Students discuss their observations with partners before sharing with the class. Step 4 is to connect the equation to their visual representations. So students write the equation, y equals 2x plus 3, which we already have written here. Together, we would identify that the slope is 2, slope is always in front of the x, and that the y-intercept is 3. We'd also re-emphasize that this format is the slope-intercept form, really highlighting to students that when you see this, slope is always in front of x, and the 3 or the number behind the operation sign would be your y-intercept. Students would then explain how each part of the equation appears on the graph. The constant rate of change, that plus 2, which they can see on the graph as well. And then they can also recognize that the y-intercept, where we're crossing the y-axis, is at 3. Rather than memorizing vocabulary, students make visual connections between the equation and the graph. This is also a good chance for you to go over rise over run. We rose by 2 each time and we ran 1. So we started at 0, then we were at 1, then we were at 2, then we were at 3. Step 5 is to write a verbal description. Finally, students write a short explanation. For example, I didn't show this, but if they select text box, they could type out their understanding and they could type the graph begins at 3 on the y-axis and raises 2 units for every 1 unit moved to the right. This is also a good time to highlight if it was a positive or negative slope. Because we moved to the right and increased, they would say positive. And just have class discussion over what they visualized here. At this time, we've shown them a table representing constant rate. We show the equation, and then we also gave them a visual on the graph where they can see that it's a linear function with no repeating x's, our y-axis where we cross the y-axis, and we still had that constant rise or that constant change of plus 2. Students have now had 5 different representations of the exact same linear relationship. They had a table, they had ordered pairs, they had a graph, they had the equation, and they've even written down a verbal description. This helps students understand that although the representations look different, they communicate the same mathematical relationship. This activity directly supports my stage 1 goals. Students develop the enduring understanding that linear relationships can be represented in multiple ways, and each representation communicates the same relationship. Students answer the essential questions right on the same workspace about how graphs, tables, equations, and verbal descriptions are connected. Instead of simply receiving information, students discover these relationships through exploration and discussion. This supports stage 2 by allowing the lesson to prepare students for the performance task. Students demonstrate the understanding by creating all 5 representations of a linear function and explaining how they are connected. As evidence of learning, students have created a graph, generated a table, identified ordered pairs, and written the equation. They've also explained the relationship using mathematical vocabulary. Students can then take a screenshot of their completed work on Polypad and upload it to Google Classroom or Canvas or any other technology. They can email it to you, whatever way that you prefer, along with their written explanation. This provides both a visual product and written evidence of conceptual understanding. I'll now demonstrate how to save and share work. After students have finished their work, they can click Save if they are logged into the Mathigon account, which allows them to save their workspace here, especially if they didn't complete it, or you have students who have extended time, or you were working with them on something a little more either scaffolded down or scaffolded up. Then for your independent workers or the students who were finishing, they can come over here to this export. It allows them to send it as a PNG, JPEG, or SVG. We'll say PNG. It's now downloaded to their desktop, and then they can email that over to you, add that to class, Google Classroom, whatever way that if you use Schoology, they can upload it there, and that way you can check and see what they've done. Polypad is an effective classroom tool because it promotes inquiry-based learning by allowing students to build mathematical understanding through exploration. Because students manipulate points, graphs, and representations themselves, they develop stronger conceptual understanding than through lecture alone. The visual nature of the tool also supports English learners and students receiving special education services by making abstract mathematical concepts more concrete. Finally, Polypad encourages collaboration, discussion, and mathematical reasoning, all of which align with the goals of understanding by design. In summary, Mathigon Polypad is an engaging and accessible digital tool for teaching multiple representations of linear functions. It allows students to create, compare, and explain tables, graphs, equations, and ordered pairs alongside verbal descriptions within one interactive workspace. By focusing on conceptual understanding rather than memorization, Polypad supports both my Stage 1 learning goals and my Stage 2 performance assessments by providing students with meaningful opportunities to demonstrate their understanding of linear relationships. Thank you for watching.